I'd like to introduce Jürgen Sturm from Intrinsic Innovation, right? Oh, yeah,
correct.
Company name was correct. Jürgen Sturm is a good old friend from our fall school. He was also joining us in 2018. In 2018, he was in robotics and in the cloud and so on. But now I'm really interested what has changed. I think a lot, or I guess a lot. So therefore, yeah. Now you have the
cool. Thanks a lot for the introduction. Yeah, it's a real pleasure to be here and also to see so many familiar faces. But of course, robotics is a small world, and so you keep meeting the same people. Yeah, so it's a pleasure to be here at the Institute and in Bremen in general. The second reason why this is really exciting is because this is actually probably the first academic talk, or the talk that we give to an academic audience on Intrinsic and its first product. So Intrinsic is a spin-off from Alphabet, and we spun out 2 years ago, but we've been operating in stealth mode until this summer, actually. And earlier this year, we made the first product announcement and then demoed the product at Automatica in Munich. And so you're seeing, this is now very fresh to everyone. And therefore, I'm also super curious actually to then hear what you think, if this is useful for you from a researcher perspective, and any other comments that you might have. So again, yeah, welcome. Let me start my talk actually with the following. So almost everything that you see around you has been produced somehow very likely by machines, and sometimes some of the things even by robots. So much of the wealth of our society, and that is actually the global society, is based on machines. The PR2 maybe did not yet contribute so much to that, but almost everything else, like the cups, the chairs you're sitting on, even the raw materials, right, have been harvested or have been produced somehow by machines. And so this is why advancing technology is so important for entire humanity, essentially. And of course, this is not something that has just happened recently, but this has been going on for several centuries, and it's called Industrial Revolution. And I thought for the first few minutes, can actually take a deeper look at that, and with the aim to actually understand what technological breakthroughs have enabled that, and what we can potentially learn for the next breakthrough to come. So, of course, Industrial Revolution has happened everywhere, right? It is a global transformation from hand labor to machine production. But not only that, also to research, the research on processes, manufacturing processes themselves, and making them more efficient, plus the development of better tools, which made it possible to produce products at scale and at a significantly lower price, so that these products then again became accessible to everyone, or to the masses. And with that, manufacturing is actually, if you look at the worldwide economy, one of the big sectors of economy, right? There is of course also housing, food and health and so on, but manufacturing itself is actually making up for much of human economy these days. And if you look more closely, right, Industrial Revolution has actually, or is considered to have happened in stages, or you can identify various stages. It started all with essentially the steam engine, and suddenly having access to mechanical power that people could use to drive machines. Right, before everything had to be hand labor or animal labor. And that enabled, for example, that the textile industry was able to produce, at scale, suddenly textiles that were very expensive before, and then made it accessible to everyone. But also technological advancements in general, like, for example, iron production got massively cheaper during this period, and which then formed the basis actually for which then formed the basis for the second industrial revolution, where the availability of iron and other goods enabled and also the invention of the railway in the first place, but the availability of iron and other things made it possible that these things could be manufactured again at scale, and so everyone could actually benefit from it. Also, gas and water supply systems got introduced. The electrification started to happen then during the second industrial revolution. And this enabled people to move between cities. And through the invention of the telegraph system, also that ideas were able to be quickly exchanged. And then the third industrial revolution, happening in the 70s onwards, and some of us have experienced, is of course the movement to digitalization, right? Everything around going from analog handwriting to digital data and data processing. On the machining side, this meant also that machines were controlled through programs. Robotics started to appear, PLCs started to appear, and found their way into everything. And then the last one is actually maybe still not clear if this is happening, but people are talking about the fourth industrial revolution, which is this shift again from machines to intelligent machines that can talk to each other, right? Internet of Things, where compute is not necessarily happening on the machine itself, but maybe anywhere. And then, of course, artificial intelligence, machine learning, which then also has an influence on advanced robotics. And even despite all of these breakthroughs and enablements, robotics today is still very difficult to use, right? None of us were here if robotics was a solved problem. And so there is still a lot of things to do. And the main problem is that it is still very hard to access, right? It takes a long time to understand how you can actually start a robot and onboard it and integrate it somewhere. It is complex to use. Every robot OEM has a different programming language, different protocols. And it is expensive to operate simply because it is so difficult to use and change. And so I'm curious through the remainder of this talk to hear from you afterwards what is actually causing this gap at the moment and what you would be missing, specifically through your researcher eyes. So what tools would you need to actually do the research, the robotics research that you actually want to do, rather than being hung up on practical problems on getting to robots to move and start up in the first place? And so looking again at the list of technological breakthroughs, I mean, there are of course many, right? But just looking at this list, the question is, what are the most recent technological breakthroughs that could become game changers for us in robotics? And we believe that, you could enumerate lots of things, but there is on one side, we have AI is now becoming a commodity, right? Everyone has access to and is using, whether they want it or not, using AI and machine learning models in your daily life. But it has not fully reached robotics in production technology at the moment. Not speaking about robotics research, right, where I guess this is everywhere. On the other hand, there have been also massive improvements, especially on the sensing side, right? The depth cameras are just a commodity these days. Also force sensing and everything got way easier. And then also compute got cheaper and smaller. So that there is actually not really a shortage of computational power on robots anymore. I mean, think of your phone, how much it can do just with a very small battery and processor. And then, of course, bringing this together, we've all seen the rise of common platforms like ROS that bring together algorithms and hardware and provide the infrastructure essentially to accelerate progress. And this is why Intrinsic was created with the goal to make industrial robotics better accessible for people who have previously, and for businesses who previously did not have access to it, simply because of the complexity and the background knowledge that you have. You really have to distinguish this now mentally from you, because you're all robotics researchers, right? You know how to get this stuff done, but the majority of people in the production sector actually do not know, right? And for them, it is impossible or extremely expensive to actually make use of that. And so, why is this white? And so earlier this year, we introduced Intrinsic Flowstate. Flowstate is the first product that we've announced that is built on top of the Intrinsic stack. This is a web-based application that allows users, and this is really not for programmers, this is for users of robotics technology, to design a work cell in 3D. And this is really about industrial static production work cells, and to program it using a graphical user interface. And I'll show you more in the remainder of this talk of how this is put together, right, and how this can be used. But it's also important to keep in mind that this is just one of the outlets that you can do when you build on top of the Intrinsic stack. But we're targeting initially people who have a need for automation technology, but who are not necessarily robotics experts. Cool. So, oops, let me continue. Good. So our platform has, or there are different aspects that went into the design of the platform itself. We're really trying to build a platform for the next generation of application developers. And so what do we mean with this? I mean, as I said, at the moment, robotics is mostly restricted to people with a robotics background. And with this platform, we're hoping to make it accessible for people who who don't have that necessarily, or who have been developing other things before in software engineering, but not necessarily have this deep robotics hardware or tech background. Second thing is we're planning to make robotics and AI accessible, and this is, I believe, where we can need your help, because there are many really good algorithms and things that would be theoretically there, but that in practice the rest of the world cannot yet use, because it is too difficult to set up and deploy and adapt to the problem that you actually have, right? Even if you're able to grasp a cup and put it in the dishwasher with a robot, does not mean that someone else who might have a robot and might have this problem of packaging cups in a basket or something could actually do the same. Third problem, I guess all of us have experienced this, to make hardware, specifically robotics hardware, better interoperable. It is always a pain these days when you add a new sensor or a new piece of automation equipment to actually connect to it and use it in your application. And we're building on top of existing standards, but simply by pulling it together and creating, making this better accessible will make life for everyone hopefully easier. And finally, with a good set of tools, we're hoping to let developers focus on the actual applications that are trying to build. So that you're not so much concerned on how your software is built, how it's being shipped, how the customer gets their updates and so on, right? That certain pieces of infrastructure are simply there and can be used by you when you're building an application or when you're developing your robotics and AI skills. So let's deep dive a little bit into the first part, build for the next generation of developers. What do we have? As you've seen from the video briefly, we're offering a web-based solution development front end that runs in the browser and that does not require any installation. I think this is really the future, right? Where people are working from different devices, and you'd like to make it accessible with as little prerequisite as possible. Second, it's hosted in the cloud initially, or you're accessing the Intrinsic Flowstate in the cloud. Once you deploy it through a robot, it of course also becomes accessible on-prem or directly. But for most part, you actually never have to worry where things are running. They're just there. Because we're part of Alphabet, all of this comes with state-of-the-art network security, right? This has been reviewed as any other Google product and service. So it's making use of common best practices, and so this is important for, maybe not from a research perspective, but for people in production. It is super important that there can't be any outage because of intruders, or you absolutely have to avoid this. And this is why most production systems are actually disconnected from the internet these days. And this is not an easy sell to tell people that they might have there are many benefits once you connect your robots to the cloud. But in the future, this will change because there are so many advantages to that. We have a web-based UI that allows you to design the work cell in 3D, configure it, and we have a no-code process editor that allows you to create your processes. We also do have a REST API for programmers because there are always parts that are missing and that you want to extend, or if you want to write your own HMI or other extensions on top, this is also possible. You can, because it's running in the browser, work from anywhere, right, which is also important of our new time post-COVID. And you can collaborate remotely with your colleagues. From a high-level architectural picture, we have some services running in the cloud. The user is connecting through a browser to our cloud services, typically, right? Starts designing, starts programming, and at some point then builds up a physical work cell in a plant or in a robotics lab, onboards it, registers it with our cloud services, and from that moment on, the user can actually deploy to such a work cell and steer and inspect and look at log files and so on. And this dashed arrow here is this last resort. If for some reason you don't have the internet or you have to disconnect it, you can also talk directly. But the more common way, and this is also how we're using it these days, is always going through the cloud services. Good. Then a second part is on making advanced robotics and AI better accessible. And this is where I said that I believe that probably all of you have some domain expertise that would form one or more very valuable skills for other people to reuse. So the basic idea is that if you have some robot behavior, it can be anything, can be sensing, can be actuation, or can be a combination of both. Anything that is reusable would form a skill. A skill can expose certain parameters that the user has to set, right? That you can't define that you can't determine beforehand. Intrinsic Flowstate ships with a particular number of pre-installed skills, like of course basic motions for robots, basic commands to control grippers, basic perception functionality like estimating poses with particular algorithms, or force-based actuation like moving into contact with a robot that has a force torque sensor, or doing some insertion. But of course, whatever list you come up with, there is always a use case that is not covered, right? And this will be the power of the community that we're hoping to build to actually extend this skill catalog. We also have, or there's obviously a way to develop own skills. For example, you could use existing libraries like OpenCV. You can use language bindings to ROS to make this as easy as possible. And in the future, it's not yet possible, also because we're not yet fully finished, to share your skills with others so that that others can then make use of that. I already alluded to that. The domain of robotics is extremely broad, right? You have industrial manufacturing, and this is where we're starting, or what we're targeting at the moment. But of course, on the other end, on the unstructured side, you have service robotics, agricultural robotics, storage, maybe medical, and so on, right? And you can imagine that in each construction robotic, using robots in construction, and each of these domains has a very particular but maybe completely distinct set of skills that you need and that people can potentially contribute. And so we've seen this before, right? No matter how you, or depending on how you think about it, but typically there's this sense, plan, act loop. And the skill sits here on the control side, obviously, but then is interacting with the hardware or potentially simulated hardware. Because it's hardware, the robot has to deal with the real environment around it. This also means that it has to deal with contact situations because we want to move or change the world. Physics plays then an important role, also modeling physics correctly, and of course also dealing with safety problems, especially when you're putting it into production use. So let's maybe first look at the sensing part and one particular skill that we're shipping with. This is for pose estimation. But again, as I said, there are plenty of computer vision algorithms that would be suitable. This one here is actually for mono RGB cameras. The user starts with a known CAD model. So in our web interface, a user can upload a CAD model of a particular part that you're interested in, that you need for your production process. We use a typical industrial camera, in this case connected through an Ethernet interface, GenICam compatible. Then in our UI, you can actually configure a pose estimator. You specify, for example, what the expected pose of the object is, what range of orientations you want to train your pose estimator for. You kick training off, and then it trains in the cloud or locally, depending on what algorithm you choose, a pose estimator. And once this is ready, you can actually use it in your process. And you can also train multiple pose estimators depending on how many parts you have or how many situations you have. For your use cases. Oops. So on the actuator side, here we have a use case on PCB assembly. So this is a PCB board into which we want the robot to insert particular components. This is one of the things that is difficult to automate today, because this insertion, you typically don't get it right, even if you're using computer vision to perfectly sense the pose of the piece, because picking it up and then putting it on a PCB board, you will never exactly hit the holes. So you need some strategy for properly inserting it. And as you can see, the approach here is now that a human is actually providing some demonstrations using a space mouse, and then the robot uses that as a starting point for reinforcement learning to actually learn a policy that has a very high likelihood of succeeding. So you can see here from the video that it is still during training may actually destroy a few PCB boards. But then once training has succeeded, this is very the robot is very soft then afterwards, or gentle to the boards. But this now, because it's packaged in a skill, makes it easy for people who don't know about reinforcement learning to automate automation problems like that, right? And this is something that hasn't been possible before. Good. Then the next aspect is making hardware interoperable. For that, maybe first to start with, we call every piece of hardware, we call a resource. So every piece of automation equipment is essentially one resource in the Intrinsic speak. A resource typically is a software service, which may correspond to a hardware driver or controller. And we provide already a number of resources, like supported hardware, you could say, in a catalog. For particular robot manipulators and grippers and cameras and so on, but this is of course also something that will grow over time. We also provide an extensible real-time control framework that allows you to not only have a hardware driver, but a hardware driver that is actually in a tight real-time loop with other real-time hardware drivers, like when you're dealing with robot control and a gripper, right? So that both of them can be synchronously used. Of course, this is not needed for every piece or every type of resource, but for two manipulators that you want to control simultaneously, you of course want to make sure that not one of them is actually hanging. This real-time control framework is using a hardware abstraction layer that allows you to integrate with existing interfaces then to your hardware. Generally, we're building on top of many existing technologies. The Intrinsic stack makes use of a container operating system similar to Chrome OS, where we run containerized workloads in Kubernetes as an orchestrator. And as part of the workloads that we're bringing up there, we're making use of Gazebo for physics simulation. It is possible, or it will be possible in the future to develop own resources. At the moment, we're still in an early phase. We're at the moment actually in a private beta. I'll show you more about that in a second. So at the moment, it is not possible to author own resources, but it will be then once we fully become generally available. Yeah, and so last section, we want developers to focus on the solution. This means that we're providing a web-based developer environment, which is no-code based, so there is no need to learn Python or C++ or any robot-specific language. It allows people to design the work cell in 3D, to author the process, then to iterate in simulation on the process and on the hardware, right? So you can check if the robot maybe does not have the right reach, you can simply swap it out. And this is a matter of seconds rather than a matter of days or weeks if you really have to physically swap out something. And then, once you're happy, you build it out in real hardware and then deploy to real hardware. And very likely, once you deploy to real hardware, you still have to check and be careful right on the first run. But this allows you to much quicker iterate and come to a working solution than before. Because the reality is, at the moment, that people design in a CAD tool, then build it, and then program after they build the hardware, right? And then it's very specific to this particular one build, and if then something is wrong, it's very expensive to change it. Good. So we also allow for more advanced authoring, so this is more or less for you. If you know how to program, you can write skills and resources, custom HMIs and other customizations. We're doing this at the moment through a ready-to-use developer container. So this is also a Docker container that you can download, and it has all the tool chains, even including Visual Studio Code, bundled with it, and a particular plugin that makes it easy then to deploy. Deploy your skills and resources to a running work cell. You can run it locally or in the cloud. We're cloud first, so we would actually even recommend that everything can be run on GitHub Codespaces, which also means that you, in the future, potentially don't need a workstation anymore, right? You can do everything in the cloud. And there is a REST API that you can use for your own extensions on top. And we've developed a bunch of developer pages, of course, documentation, including tutorials and videos for showing people and guiding people to how to use that. As I said, at the moment we're in private beta, so a few people, or the first batch of people now got access to that and is now walking through a bunch of these tutorials. One of them is to actually stack a few Jenga blocks to a small tower. The task then at hand is to first build or to lay out a work cell, adding a UR robot, adding a gripper, adding a camera, creating a simple process then for pick and place, which makes use of pose estimation through a wrist camera on the robot, but theoretically users can mount the camera anywhere where they think it is convenient. And then moving into contact and picking up a Jenga block, placing it in a different location. And this can be completely developed and tested in simulation, and then users can actually deploy it to real hardware. At the moment, because we don't have compatible hardware that we can easily ship, we actually set up a bunch of robot cells, both in Munich and in Mountain View. And so the beta testers can then reserve slots on these machines and then play with Jenga blocks remotely, but on a real robot. And I think that that's another game changer that people are now realizing. You can actually program robots remotely. First of all, because you're doing it in simulation, but second, because you can just dial into a work cell and do your stuff there. And this really has not happened before, I think. Good. So let me show you a few more features. Unfortunately, I am not able to show you a live demo today, but I can show a few more video footages here. If this loads. So this is the standard web interface that people see after they log in. Yeah. Let's see, where is my mouse pointer? Yeah. So you have the work cell design. This is already a quite elaborate work cell, as you can imagine. In the easiest case, you would just have one robot arm with a gripper on it, and on the left-hand side, you see the process. Yeah. When you after you log in, you get to this welcome page where you see your recent solutions or recent applications. You can create a new solution, either starting completely from a blank sheet or from a particular example. And then, this brings up this 3D workcell editor, where you might have initially nothing, and then you start uploading your own geometry of your workpieces or the things that you want to manipulate. You add assets, which are the resources that you saw earlier. You can add different types of robots, different grippers to your workcell. And it's important that a resource actually brings all the parts that are needed for controlling it. It's the hardware driver, it's the sim driver, it's the geometry, right, and the configuration, so that it can actually fully work in simulation, but then also on real hardware. But once you put everything into your scene, you can then, you have the scene tree here on the right side, where you can reparent objects, drag and drop, for example, so that the gripper is mounted to the flange of the robot. So you connect all your pieces. And then when you're happy, you can actually come up with also with big scenes. Then for every piece of equipment, you can actually, on the left side, you see a properties panel where you can then change the configuration. For example, for a camera, you can overlay a camera frustum just to see what the camera sees. You can start camera calibration or type in the camera calibration parameters yourself, depending on where you're getting them from. But we do have integrated wizards for intrinsic and extrinsic calibration. So intrinsic calibration for the internal parameters, and then robot to camera calibration if you if you have a hand-mounted camera, for example, or a static camera that you want to calibrate with respect to a robot. And this is super useful because, I mean, I assume everyone who worked with ROS and cameras has used this before, right? You get an overlay between the real world and your digital twin, so that you can verify that everything is correct. Then next part is that you have to write the program. It's actually interesting, we're using behavior trees in the back end, but we're visualizing it almost as a flow chart. But the reason why we're not representing it as a flowchart is because flowcharts tend to become like spaghetti code. You can have arbitrary arrows, and the tree, a behavior tree, by definition, has a certain structure, right? You can't suddenly jump from one node to a different node somewhere else, but you always have to go through this hierarchy of commands. And then from here, you add skills, you parameterize your skills, you choose, for example, on which robot or which piece of equipment do you want to run this. In this case, the robot is supposed to go to a particular target frame. You select the speed, the contact force that you want to achieve, and then you can run it with just one click. We also have a jogging interface so that you can pose the robot and jog the robot. And there are control flow commands, for example, for adding groups, branches, parallel execution, and so on. This is, I think, such a user interface is really nice for people who don't have a programming background, right? For creating quickly a small process. But of course, the bigger your process gets, the more tedious this might become, right? And then from a certain complexity on, you might actually want to use a different interface. But at least for getting started with it, this is a great way for building something. Plus, you can structure it in groups, and you will also be able in the future to reuse certain parts of your tree. And in that way, you can actually compose it from existing building blocks. This is now showing again the pose estimation. We want to detect this part here as part of the production process. And we briefly had this before. So you can create a pose estimator. You have to select for which object you want to train, from which camera, and what type of detector you want to train. You can specify the view range from where you're expecting to see the object. You kick off training, and then it either runs on-prem or in the cloud, depending on how much GPU resources you need. And then you have a pose estimator trained for this particular object for a particular camera in your scene. So. Good. And as one at Automatica, we actually, had different booths where we showed how the developer experience itself looks like, how perception works, and force-sensitive grasping. But we also had one big industry use case set up there, which is pretty amazing because you have to imagine two big robots that were assembling part of an electric vehicle. And Comau is a system integrator actually that works with Stellantis and other automotive companies to create such production lines. And this robot here is mounting essentially this electrical component here on a larger metal frame. And it's doing this without fixtures. Uses pose estimation for picking up nuts and for picking up this piece and placing it using force-sensitive guidance into the frame. Whoops. Good. So we're still in this beta phase. If you're interested, you can sign up there. And our plan is now over the next few months to enroll more and more people. We're doing this gradually because we know that the system is not finished, right? And we don't want to frustrate people now by opening it up too quickly. But over the next few months, I assume that more and more people will get access to this. And then hopefully in the foreseeable future, this will be open to everyone who wants to use this. So, wait, how are we doing in time actually? Okay. Okay, very good. So just as an outlook, right, of other things that are going on at Alphabet and that can or might become useful for integration with such a system is, this is from DeepMind in London, where a robot is supposed to help with household tasks. So I assume Michael or some of you might be familiar with this work as well. And the idea here is actually to use ChatGPT or BART, large language model, to generate instructions for the robot of how to achieve this task. Right? The human says, please clean up the mess that I created. And so the robot queries a large language model with essentially the question, how can you help me to clean this up? And then it also gets conditioned on the start of the sentence where the robot says, I would do this, and then the language model completes the sentence essentially in the instruction, and you create instruction by instruction, and for every instruction, it also then queries a second network that knows about the skills or the affordances what the robot can do, and then partially manages to clean it up. It is very exciting, but I think also still early work, but potentially something that will make it possible that robots become much more versatile in the future. Oops. Another work here is on soccer playing robots. The interesting part here is that these robots completely learned walking in simulation, and you really get these controllers that can surprisingly well react to disturbances, I might have to skip here in the video to a different location. Yeah, so you have a really high-dimensional problem. The robots are trained initially on two tasks, namely to stand up from the ground and to score a goal, right? And then based on these two skills, the robots actually develop this emergent behavior of actually being able to play soccer and get up. And because of a good physics simulation, but also these disturbances in simulation that they've been trained on, they are able then to reproduce this in the real world without adaptation. And then here is another work. This has happened at Intrinsic, but also together with other groups at Alphabet on multi-robot coordination, where you have such a high-dimensional planning problem that you actually can't efficiently come up with the best trajectory that is collision-free. But you can train a network that for a particular scene that is able to control these 4 robots in a collision-free way to reach certain welding spots. But either way, the main point here is that there is enough stuff going on both inside of Alphabet, but of course also everywhere else in the world, where people have developed great skills and capabilities that would that other people probably could benefit from if they had access to it, right? There is a real transfer problem essentially from one person who understands how to do this to another person who has the need for actually doing this. And so bringing these 2 parties together is really a big opportunity. Intrinsic joined forces with Open Robotics earlier this year. So, and there's of course also interesting stuff going on. A new ROS version was released recently, as well as a new Gazebo version. And this development continues. Yeah. So Flowstate is, as I said, the first product built on the Intrinsic platform. It's not fully finished yet. We're today right here in the middle, you could say. You know, we already have this intuitive developer experience. We have some AI capabilities and skills and a way to extend that. We have a state-of-the-art infrastructure platform, I would say. The framework for robot-agnostic control, so the framework is there. We have some robots supported, but it is not yet open for developers, external developers, to actually add their own robots. But this will come now soon or after the beta has finished. Good. So to summarize, you've seen the Intrinsic platform. Hopefully got a sense for the AI capabilities that we have, but also what AI capabilities we're missing. Hint. And we had a break in our research internship program last year, but this summer we again have a few people visiting, and I assume that for next summer this will actually expand. So if you're interested, feel free to reach out to me or to Stefan Schaal, who is our scientific advisor.